And we're back. Welcome back from the weekend and happy Tuesday. Today we're going to switch gears and look at the normal distribution, which is probably the hero of this probabilistic and statistical world. Before we do so, some administrative bits. The reading has updated by the 24th of this month, which is a week from today. Please make sure you're reading sections 2.4.2 through 4.3 in the main text. That's pages 89 through 95. It's only 6 pages, not that much. Please make sure you're keeping up with the reading. Including today, there are 5 class meetings left. Written exam number 2 for this class will be this Thursday at noon, administered over 30 hours to be handed in electronically via Blackboard. Residence halls will close Wednesday, the 25th. That's the day before Thanksgiving at 5 p.m. If you are on campus, make sure you are adhering to that. I have no control over it. You must vacate the residence halls and you do not return back until the spring semester. The last day of classes will be Thursday, December 3rd. Reading day is the day thereafter. Dr. Asami should be sending out messages about Division Day when everyone presents their presentations for project work in front of the entire division. The scheduled exam period for this class will be Tuesday, the 8th of December, in the block of time between 10:30 and 12:30 in the afternoon. During this time, we'll be having project presentations. We have a final project for this course, and you'll be presenting your project work during the scheduled final exam period. The last day of classes will be the 8th, Friday, the 11th of December, and you'll be passing in via Blackboard your final project, so you write up the code, the experiments, and so forth on the 11th, which is the last day of finals at 8 p.m. Okay, so why don't we begin? So when we think about the natural world around us, we have all sorts of quantities like light, pressure, heat, sound energy. Let's take a look at interesting vibrational mechanical energy. Now, this is an interesting experiment. It really works. You can make some homemade Play-Doh, get some flour, mix it in water, get it a little bit thick, put it on a piece of saran wrap on a speaker, play your favorite music, and you'll see it dance around. And so there are certain types of properties typically associated with the physical world and the natural world that exhibit what we're going to call inertial qualities. And so for inertial, what we mean is that the immediate future state is determined by the current state. So what do I mean by that? What I mean is that if you're looking at the temperature for the next instant in time is the temperature for the current instance of time plus or minus some small amount. And so you can very easily predict what the next temperature is from the previous temperature. It just doesn't jump around to an arbitrary value. It doesn't go from, say, 58 degrees during the daytime. All of a sudden, the next instant, it's 120 degrees. That's not how temperature works. And so this quality where the future value or future state is determined by the current state is called inertial. And so any inertial quantity that we measure or talk about is well defined by this so-called normal or Gaussian distribution. And because things like temperature, light, pressure, position, mechanical force, and so forth is an uncountably infinite quantity, we call any kind of stochasticity that we measure for changes in those inertial values, we're going to use a density function. And this density function specifically is the density function for the normal distribution governing inertial quantities, these real valued quantities that are inertial. And that just happens to cover majority of quantities dealing with physical world or the natural world. And so there's our density function, f of x, and sometimes I'll use p of x as a synonym, but f of x is 1 upon radical 2 pi sigma squared e to the minus 1/2 quantity x minus mu squared. And so if you were to draw this out, it looks like the classic bell curve, and these hump is what we call the mode, or the largest probability associated with this density. And then we have the center here, that's our mean, mu. And so mu is often called the center of mass because it is the center point where all the mass is collected, the balance point, as it were. And so if we take our variance, sigma squared, the square root of that is our standard deviation, sigma, that standard deviation tells you some measurement above and below the mean by which all of the observations will vary. And so away from the mode, we have these extreme parts of our distribution on the high end, on the right, and on the low end, on the left. And these are called the tails. Here's one tail, and here's another tail of this distribution. And so oftentimes when we talk about the parameters of the density for the normal distribution, it has two parameters that govern it. One is called the mean, mu. So there's mu in our density. And the other is the variance, the square root of which is a standard deviation. So there's sigma squared. Now, it just so happens is that when you manipulate or change the mean and the variance, you're changing with the mean how much your center of mass is shifted to the left or to the right. And in effect, what you're doing is you're changing the location of your distribution. Where is your distribution centered? And so this mean, mu, is often called the location parameter. And then when you also change the variance, sigma squared, you change the standard deviation, the square root, you're making it more and more dispersed if sigma squared increases, and less dispersed if sigma squared decreases, is smaller. And so this changes the scale of your distribution, and hence sigma squared, or the variance, is often called the scale parameter. And so the two parameters that at a coarse level describe the shape of your normal distribution are called the location scale parameters, mu, our location, and sigma squared, our scale. Okay. And so the normal distribution, and this is a typo, that should say 1/2, the normal distribution has an interesting property associated with it. When you add up the area under the curve for the normal distribution, a certain number of multiples of the standard deviation above and below the mean, center, you get a certain percentage of the total probability underneath that probability density. And so if we go plus and minus 1 standard deviation, so here's mu, here's a point, we're going to call that mu plus 1 standard deviation. There's a point to the left, and that's called mu minus 1 standard deviation. We could also write that as mu plus or minus sigma. Well, in that interval between mu plus or minus 1 times our standard deviation sigma, we find, if we were to do that integral, about 64% of the probability mass. If we go 2 standard deviations, well, we're going to add to that another 26 or 27% roughly of the probability distribution. So if we take our 64 and we add that 26, that's about 80%, almost 80-something% of the probability mass. And it just so happens, let me verify that. 46, that's 2, it's 1, 8, about 90 to 93% of the probability mass. So if we go plus or minus 2 standard deviations above and below the mean, so mu plus or minus 2 standard deviations, well, that's our 64.2 plus another 27.2, that's 4, that's 11, that's 91.4% of the total probability mass. And so there's a really neat relationship between the interval as a multiple of the number of standard deviations above and below the mean and the probability underneath the curve within those bounds. Now, of course, you might be asking, well, why is this even useful? Well, if you look at this idea of outlier detection, how do you determine whether or not some value is typical of what you'd usually observe? You would use this fact, this relationship between the percentage of total probability and the interval above and below the mean to do this outlier detection, some distribution over typical heart rates, for example. And then you want to detect if some heart rate is abnormal for that person. So you collect a bunch of measurements for normal heart rate for that person. You calculate a distribution, normal distribution, because this heart rate is inertial. And then when you take a new heart rate measurement, you test its value against this interval. And if that value is outside of 95% of the set of values for this distribution, or governed by this distribution, then it's considered an oddball. And so you can use this relationship between the probability mass under the normal distribution and the intervals, multiples of the standard deviations above and below, to do this outlier determination of whether or not some measurement is an oddball or an outlier. Okay. And so because this is a density function, we know that the law of total probability should hold, and we're going to demonstrate that. And then we also are going to prove that the mean or expectation of this normal distribution is mu, and the variance is sigma squared. And so because it is a density function, we use integration instead of summation. So here, expectation of x is just x times the density function, dx, where the density function is 1 upon radical 2 pi sigma squared e to the minus 1/2 x minus mu quantity squared over sigma squared. And we're going to plug that in also for the variance, x minus mu times that density function. And we're going to show that the expectation or the mean is mu and the variance is sigma squared. Okay, so let's take a look at total probability. So total probability says that if we integrate between minus and positive infinity for the density function, that we get 1. Now, the one caveat here is our variance sigma squared is always positive, right? You can't have negative variance. It always is positive, or it could be 0. If it's 0, that means we have what's called a point mass. A 0 variance looks like the following. Here's mu, and then here is your single data point, and all the probability, P of x equals 1, is on that single point. So that's what a 0 variance distribution looks like. And so in general, for the non-degenerate case, the variance is going to be greater than 0. So my variance, sigma squared, is greater than 0. Okay, so let's do that integral. We have the integral from minus to plus infinity, 1 upon radical 2 pi sigma squared e to the minus 1/2 sigma squared, 1 over 1/2 sigma squared times x minus mu quantity squared. That sigma squared is in the denominator, of course. And so we do that integral, and we notice that 1 over 2 pi sigma squared, radical sigma, 1 over radical 2 pi sigma squared is a constant. So we bring that out from behind the integration, and we're left with that leading coefficient, 1 upon radical 2 pi sigma squared, integral from minus to plus infinity, e to the minus x minus mu quantity squared upon 2 sigma squared dx. Okay, so now we're going to do a u substitution. So we're going to let u equal x minus mu upon radical 2 sigma. And we're going to do that because we want to express u squared because it's convenient for us. So that means through the Jacobian, du is equal to 1 upon radical 2 sigma, because in the numerator we have x to the 1 power, and we do that du dx, that x to the 1 power goes away, goes to 0, or goes to 1. And this mu is a constant, so that goes to 0. And so we're left with du is 1 upon radical 2 sigma dx, or radical 2 sigma, if we multiply both sides of equality by radical 2 sigma, we get radical 2 sigma du is equal to dx. So there's our substitution. All right. So we're going to do the substitution. And so we're going to say e to the minus u squared, because if we look at this expression, the exponent, the original exponent for e, well, if we take the square root of that, that's just x minus mu upon sigma squared. That's sigma if we take the square root, and then we have a square root of 2. Okay, so we do that substitution. We say e to the minus u squared du, and then when we make that u substitution through the Jacobian, we include a factor of radical 2 sigma. All right, so now we have this expression, and we're going to factor out this radical 2 sigma out from underneath the integral because they do not involve u. They're constants for all intents and purposes. So we're left with that original leading coefficient, 1 upon radical 2 pi sigma squared, radical 2 times sigma, our integral from minus infinity to positive infinity, e to the minus u squared du. So we carry out this integral, our integral between minus and plus infinity, e to the minus u squared du. That's just nothing more than the Gaussian integral. And so this Gaussian integral, I'll leave it to you to watch this YouTube link to fill yourself in about the Gaussian integral. So for now, for this class, just take it on faith that it is true, because it is, but you can certainly encourage you to go to consult this video to look at the derivation of the Gaussian integral. Okay, so we make that substitution for the Gaussian integral, and we get our original coefficient, 1 upon radical 2 pi sigma squared, times radical 2 times sigma times radical pi. Now, of course, the sigma here is the same as saying radical sigma squared. So it means we can replace this sigma with a radical sigma squared, and now we have this product here where the same thing in the numerator is also in the denominator. So that's just nothing more than 1. So we get this, we get 1, and that's this 1 is exactly the result we're after, proving that the law of total probability for the Gaussian density function, or the normal density function, or normal distribution, is exactly 1. The law of total probability holds. So let's take a look at the mean. So we set out to prove that the expectation of the normal distribution is equal to mu. So we set up our expectation, e of x, that's x, times the density function f of x dx. And so we're going to plug in for the density function. We get our integral from minus infinity to plus infinity, x times our constant, 1 upon radical 2 pi sigma squared, e to the minus 1/2 x minus mu quantity squared upon sigma squared dx. Okay, so now we're going to do a factoring, and we're going to bring this constant out from underneath that integral because it is constant, does not involve x. So we get a leading coefficient, 1 upon radical 2 pi sigma squared, our infinite integral from minus infinity to plus infinity, x e to the minus 1/2 x minus mu quantity squared upon sigma squared dx. So now we're going to do a u substitution. We're going to say, call y x minus mu, because we want to make a replacement here for this exponent for that e term. And so if we take the derivative of both sides for that y substitution, no longer a u substitution, we have dy is equal to dx. Okay, so there's no constant factor when we change the variable of integration. But we also can manipulate this equation, and we get x is equal to y plus mu. So let's go ahead and make those substitutions. So we're going to substitute two things for this x. We're going to substitute y plus mu. And then for this x minus mu, we're going to substitute y. So let's do that. We have our leading coefficient, 1 over radical 2 pi sigma squared, our integral from minus infinity to plus infinity, y plus mu times e to the minus y squared upon 2 sigma squared dy. So there's our substitution here. We're reflecting both the u substitution as well as the Jacobian when we have that dy. And that constant factor just happens to be 1. Okay, so now we're going to make an observation. We have two terms here in this parenthesized expression. We're going to multiply this e term to each one of them. We're going to multiply by the first term, and we're also going to multiply by the second term. We're going to distribute this multiplication by e to the minus y squared upon 2 sigma squared over the first and second terms in this parenthesized expression. And so we do that with the second term first, and we get this leading coefficient, mu, times e to the minus y squared upon 2 sigma squared dy. So when we do that, well, that's just the same as 1, because if you notice here, this coefficient and this e term dy, well, that's just the density function for the normal distribution. And we said when we integrate it between plus and minus infinity, or I should say more correctly, minus and plus infinity, that's just 1. Law of total probability told us that. So that's just mu times 1, which is our result for that second term. So now we focus our attention on that first term in the parenthesized expression. We have our 1 over radical 2 pi sigma squared. We have that integral from minus infinity to positive infinity, y times e to the minus y squared upon 2 sigma squared dy. And so if I do that out, I collect my terms. There's my leading coefficient, and there's my y under the integral e to the minus y squared over 2 sigma squared dy. So now I'm going to look at this integration. Let's consider this so-called odd function. We're going to take a little bit of a segue here. You'll notice whenever y for this integral is negative, well, the value of this expression is negative. Whenever it's positive, the value of this expression is positive. So this is what an odd function looks like. An odd function takes on negative values when the domain is negative, and it's also symmetric about the origin. Here's my origin. And so that means the area under the curve for this region on the positive side is the same as the area under the curve for this region, only the area under the curve for the region less than 0 is going to be negative. So it's symmetric about the origin. And so we have the same area, only one is negative and the other is positive. So let's take this odd function, our integral for it, between minus infinity and positive infinity, and let's break it up to the negative side. Here's my negative side, so it goes from minus infinity to 0, y e to the minus y squared upon 2 sigma squared dy. And then we have the positive side, which is our integral from 0 to infinity, y e to the minus y squared upon 2 sigma squared dy. Okay, so let's define a u substitution, and let's let u equal y squared upon 2 sigma squared. So if u equals y squared upon 2 sigma squared, we take du dy of this substitution, and we get du is equal to y upon sigma squared dy. We can multiply both sides by sigma squared, and we get sigma squared du is equal to y dy. So everywhere we see a y dy, when we do our u substitution, we're going to substitute that by a constant factor sigma squared du. All right, so there's our Jacobian. So here, what you'll notice, for both halves of this odd function for this integral, we have a y dy. So it says wherever we see a y dy, we're going to replace it with a sigma squared factor times du. So let's do that replacement. So we have a sigma squared du for the negative part of that integral for the odd function, and then we have the sigma squared du for the positive part of the integral for that odd function. Okay, so now we're going to take these expressions and we're going to look at this u substitution. And we said let u equal y squared upon 2 sigma squared. So there's a y squared upon 2 sigma squared for the negative part of the odd function and for the positive part of the odd function. So let's do that u substitution. So now we're left with integral from minus infinity to 0, sigma squared e to the minus u du, plus our integral from 0 to infinity, sigma squared e to the u du. All right. So now let's just look at half of it, because we know that whatever the area under the curve is for the positive side is going to be the same area negated for the negative side. So we really only need to care about half of this odd function. So let's look at the positive half. So we have our integral from 0 to infinity of sigma squared e to the minus u du, and we're just going to evaluate that integral. Well, it's a straight solving of that integral, and that's just minus sigma squared e to the minus u. And so we're going to solve for that indefinite integral using the definite integral, and we'll substitute for u at the bounds of the integration. So we do for u equals infinity, we substitute into that expression here, and then we subtract from it the evaluation for u equals 0. So for u equals infinity, it's negative. So that term doesn't count because you have e to the minus u, right? And that's just an infinite negative exponent, so it goes to 0. And then for u equals 0, we have 1, and we're subtracting that value of the expression evaluated at u equals 0. So minus of minus is plus, and we have sigma squared times e to the 0 power, which is just sigma squared. Okay, so we have sigma squared is the area for the positive part, and we know that the negative part has the same area negated. So for the negative part, that's minus sigma squared. For the positive part, that's sigma squared. So that's just 0. And there's our area for this odd function. Okay, so there's the area for this odd function, and we're going to use that fact in our original expression that we had when we're trying to solve for the expectation. So we had our expression set up for the expectation, and we had that substitution with this parenthesized expression y plus mu. And so here we have two things when we multiply this e to the minus y squared upon 2 sigma squared dy times each term in that parenthesized expression. So here we have y times e to that power, and we have 1 over radical 2 pi sigma squared integrating from minus infinity to plus infinity. Well, we just said that this expression is the same as multiplying the first term times this, e, times that leading coefficient, and then we had this other term, the y term, times e times that leading coefficient dy. So we have this leading coefficient, 1 upon radical 2 pi sigma squared, our infinite integral, from minus infinity to plus infinity, and then we have that y, e to the minus y squared upon 2 sigma squared dy. Okay, so now we're going to make use of the fact that this is an odd function, and we just got done in the previous page showing that this odd function has an area under the curve which is 0, this particular odd function. So that's going to go to 0, and we're left with mu times 1, which is just mu, proving that the expectation of our normal distribution is just mu. All right, so let's take a look at the variance. So for the variance, we're going to set up our expression for the variance, which is just the difference between each measurement, x, and its mean. We already know what the mean is. The mean is just mu, quantity squared, because we care about the magnitude and not the direction of the dispersion. And we're going to weight that by our density function f of x dx. And we take the integral from minus infinity to positive infinity, and we're going to prove that this is equal to sigma squared. And so we're going to use the same density function. That's the density for the normal distribution. And we're going to start out just setting it up by substituting for the density. So in place of f of x, we're going to write our 1 upon radical 2 pi sigma squared e to the minus 1/2 quantity x minus mu squared upon sigma squared dx. So now we're going to make another substitution. We're going to do another u substitution. Well, in reality, this is a y substitution. So we're going to say let y equal x minus mu, because we want to get rid of this term in the exponent and do something to simplify this leading x minus mu quantity squared. So we're going to let y equal x minus mu. We take the derivative of both sides, dy dx. That equals dy is equal to dx, because here we have this x to the 1 power. So that's going to go to 1, and this mu is a constant. So it's going to go away, go to 0. And then we also can do a little bit of algebra on this y substitution. We get x is equal to y plus mu. So now we're going to make that substitution. So y is equal to x minus mu, so we call that x minus mu quantity squared. We'll call that y squared. And then we have x minus mu quantity squared. That's also y squared. So with that y substitution, we get our infinite integral from minus infinity to plus infinity of y squared, our coefficient 1 upon radical 2 pi sigma squared, e to the minus y squared upon 2 sigma squared dy. So this radical 1 upon radical 2 pi sigma squared, that is a constant, so we factor it out of that integration. So we get that leading constant, 1 upon radical 2 pi sigma squared, our integral from minus infinity to plus infinity of y squared e to the minus y squared upon 2 sigma squared dy. So we're going to solve this using integration by parts. And how we're going to do this is we're going to choose our f of y term, that's just going to be y, and we're going to choose our g prime of y term, that's going to be y e to the minus y squared upon 2 sigma squared. And of course, we choose our f of y term because when we compute the f prime of y term, that y function is going to go away. And so f prime of y is equal to 1, and g of y is the integral of g prime of y. That integral is just minus sigma squared e to the minus y squared upon 2 sigma squared. And so now we have everything we need to do the integration by parts. So we have in our first expression, we have our f of y times our g of y. So our f of y, that's just y. That's our f of y. And then our g of y is minus sigma squared e to the minus y squared upon 2 sigma squared. So it's minus sigma squared e to the minus y squared upon 2 sigma squared. And we're going to evaluate that between plus and minus infinity. The next part, that's of our integration by parts. That is our prescription that says the integral of f prime of y gy dy. And so here we have our leading coefficient, and then we have our f prime of y, which is 1, and then we have our g of y, which is our minus sigma squared e to the minus y squared upon 2 sigma squared. So in our integration by parts, remember, we said that our integral was equal to f of x, g of x, minus the integral f prime of x, g of x, dx. And here we have y instead of x. So that would be f of y times g of y minus integral f prime of y, g of y, dy. And so because in the second portion we have a minus sign, if we have minus f prime of y, g, y, well, f prime of y we said is 1, g of y is equal to minus sigma squared e to the minus y squared upon 2 sigma squared. Well, this term, dy, is just negative, so minus and minus, that makes it plus. And so we get this plus sigma squared, 1 upon radical 2 pi sigma squared. These are both constants, so we factor those out, and then we're left with integral from minus infinity to plus infinity, e and then we are left with our integral from minus infinity to plus infinity, e to the minus y squared upon 2 sigma squared dy. And so if we do that integral, well, this term is just how the hell did I get that? Hmm? So if we do this evaluation, let's see what we get. Well, this first term, that's just 0. If we evaluate y is infinity minus this expression for y equals minus infinity, well, for infinity case, that is just e to the minus some power that's infinity. So minus some power that's infinity, because it's y squared, that's just 1 over e to some large power. So that term is just 0. In the case where y equals minus infinity, well, it's y squared here. So that's still e to minus some large power, and that's 1 over e to that large power. So that's the 0, so it's 0 minus 0. So this term, that first term, from our integration by parts, that's going to be equal to 0. So now let's turn our attention to the second term for integration by parts. Well, for that second term, well, we have here our leading coefficient. We have our infinite integral, minus infinity to plus infinity. And then we have our e to the minus y squared upon 2 sigma squared dy. Now, of course, this is the same as our density where mu is equal to 0. And so that is literally an application of the law of total probability. So this expression, this entire expression, is just 1. And so that's sigma squared times 1, which is just sigma squared. And there's our result, sigma squared. And this proves that the variance of a normal distribution is nothing more than sigma squared. Okay. And so in closing, the normal distribution is governed by density function because this inertial measurement, whether temperature, pressure, light, so forth, position, velocity, is uncountably infinite. And this density is a proper probability density. It obeys the law of total probability. If we integrate that density between minus and plus infinity, integrates to 1, the expectation is mu, and the variance is sigma squared. So with that, we will end there. Please make sure you're keeping up with the reading, and please make sure you're staying on top of these key dates. So we'll end there, and as always, please stay healthy, stay safe, and I will see you all on Thursday. Thursday, we'll be going over the take-home exam.